Welcome to Module 6 on finite volume method. We had discussed earlier one spatial discretization technique that was based on finite difference method. We had a detailed look at how do we approximate the derivatives in a partial differential equation at a given grid point and thereby obtain a discrete form of a continuum problem. And we also learned different approximation techniques. We saw its application to two scalar transport problems. In the beginning of this course, we said we are going to have a look at three prominent discretization techniques, that is finite difference, finite volume and finite element method. So today is the second such discretization scheme which we are going to discuss in the next few lectures. So the outline of this module, we would have a look at a basics of finite volume method. It involves approximation of a set of integrals which we call finite volume integrals. So we would have a look at the approximation techniques for finite volume integrals. The evaluation process also involves the interpolation of the function values at computational nodes. So we will see which are the interpolation techniques which are commonly used in the context of finite volume schemes, and towards the end of this module we will have a look at applications of finite volume method to scalar transport problems. The first lecture in this series we will focus on the basics of finite volume method. Now what is the basic motivation of finite volume method? If you remember, we learned in our mathematical modeling that we have got the basic conservation laws of physics expressed in an integral form. This is how we derived it, starting from the conservation law expressed for a system to the corresponding integral form for an arbitrary control volume. So we have already got a form of equation which is available, and the choice of control volume we said is arbitrary. Can we extend it further and divide a problem domain into non-overlapping set of control volumes? And if we can do that, our conservation laws would be valid in each one of those control volumes. Can we make use of this feature to come up with a discretization scheme which can help solve our problem? And if we can do that, we won't be limited to the Cartesian grids which we required for finite difference method, or the other way which we had for complex geometry for finite differences. We said we have to go for a mapping, a map or complex problem domain into a conceptual rectangular computational domain. That mapping was fairly complicated, may not be possible for all set of geometries. So now here we have got an opening, but look, we have got an equation expressed in integral form. Now that integral, by the basic law of calculus, is that it could be broken down into small integrals over a smallest subset of finite volumes. And in fact what we can say that conservation law has to be valid over each one of those small control volumes which could be of arbitrary shape, and our complex domain can be represented by a union of such non-overlapping control volumes. So that was the starting point. The further motivation was provided by developments in finite element method. Let us have a brief look at it on our board. What happened during the early days of our development? So let us call this inspirations of finite volume method. Finite volume method. Now you can recall one more thing from a fluid mechanics, that we had what we call a method of integrals. Integral finite volume, or rather we call it did control volume analysis. In fluid mechanics. And this is one method which is used in obtaining the design variables or to get a gross overall features of a fluid problem. Now next one we said, look, in 1960s, by end of 1960s, a finite element method was well established for structural problems. So irrespective of the complexity of a solid domain or the structural domain, in finite element method what we can do is we can divide the domain into small subdomains of what we call finite elements, and these elements could be of any shape. These could be triangulars or they could be rectangles or they could be of arbitrary quadrilaterals. So we can have any choice of these elements in finite element analysis, and to deal with such problems there were lots of development in unstructured grid generation. So unstructured grid generation techniques were available to decompose your complex problem domain into a set of non-overlapping finite elements of the chosen type. So in early 1970s, there was a group at Imperial led by Professor Brian Spalding, who is most famous student is Professor Patanka. They came up with, or they promoted, this finite volume method. They said, look, our integral forms, they were expressed for an arbitrary control volume, that's over which we express our conservation laws. So our given problem domain can be again divided into smaller subdomains or smaller control volumes, similar to the way we do in finite elements. The technology for that is available in unstructured grid generation techniques, okay, and make use of the basic conservation principles or satisfaction of the conservation principles at each one of those smaller control volumes. Okay, so from the beginning the finite volume method is based on the approximate solution of the integral form of the conservation equations. Now this integral form of the conservation equation is available the way we have derived in our mathematical modeling module from the first principles. And then what we can do is, the way we just described, the problem domain is divided into a set of non-overlapping control volumes, and these control volumes, since they were finite volume, they were called finite volumes, and we can now apply conservation equations to each of these finite volumes and take all of them together to obtain a system of discrete algebraic equations which can be solved in the same way as we did in the case of finite difference method to obtain solution to our problem. And these integrals which occur in application of conservation equation to each of the finite volumes, they are expressed or they are evaluated in terms of the function values at what we call computational nodes. Now, there could be one question here, that yes, we derived our conservation equation in integral form, so we have the wherewithals to proceed with the application of finite volume method, but suppose we had the conservation equation in differential form. Now, suppose we did not have the integral form of the conservation equation, suppose we were given a differential form del of rho phi over del t plus divergence of rho v phi is equal to divergence of gamma times gradient of phi plus our volumetric generation rate, let us call it q phi. So, this is our differential equation. Now, if you want to obtain an integral form, we can do the reverse process of what we followed in the derivation of the differential form of governing equations starting from the integral form. So, let us integrate this equation over an arbitrary control volume. So, integrate this equation over an arbitrary control volume. CV could be of any shape and size. So, del rho phi by del t. Now, this is summation here, so we can now write each one of these as separate integrals. Divergence of gamma times gradient of phi d omega plus volume integral over CV of q phi d omega. Now, CV were fixed, we can now interchange this time derivative and integral operation. So, for a fixed CV del by del t and integral over CV d omega, they commute. So, that is why we can write this integral of rho phi by del t d omega over CV. This is time derivative of rho phi d omega over CV. Now, these two integrals which involve the divergence operators, they correspond to convective and diffusive fluxes respectively. Now, these can be transformed using Gauss divergence theorem. So, Gauss divergence theorem would give us that integral over CV of the term divergence of rho v phi d omega, this is equal to the surface integral of rho phi v dot dA over this control surface, and similarly divergence of gamma gradient of phi d omega over Cv. This is equal to this surface integral gamma times gradient of phi dot dA. So, if you substitute all these three, so equation 3, 4 and 5 into 2, substitute 3, 4, 5 into equation 2, then what do we get? Del by del T of rho phi d omega over Cv plus surface integral over Cs of rho phi v dot dA is equal to surface integral over Cs of gamma gradient of phi dot dA plus volume integral over Cv of q phi d omega. So, now this is the integral form integral form required for finite volume analysis. So, if we had the integral form per se available with us, that is fine. If not, if we only had the partial differential equation given to us in the form of equation 1, we can take this partial differential equation, convert it into a conservative form and then integrate it over a control volume to obtain the integral form of the conservation equation suitable for finite volume analysis. Okay, now let us see what are the attractive features of finite volume method. Now, what we saw from the very beginning, that look, we can now have any type of decomposition of a problem domain. So, that is why the finite volume method can accommodate any type of grid, and hence it is naturally suited for complex geometries. Okay. And this explains its popularity for commercial CFD packages. You take any commercial CFD package with Fluent or Star City or similar softwares, they are all based on finite volume formulations, because they must cater to the industrial problems which are defined in complex geometries. And the advances in unstructured grid generation method, they have made the application of finite volume to flow problems in arbitrary complex geometries very simple. Similarly, for large scale flow problems which are to be solved on parallel machines, there are mesh partitioning technique, there are geometric and say mesh partitioning techniques developed for finite element analysis. These can be applied as such to finite volume grids to make a finite volume code run on a parallel machine. So, these two developments, the developments in unstructured grid generation methods and mesh partitioning techniques, which were originally developed for finite element method, they can be directly used in finite volume method, and they have contributed greatly to the popularity of finite volume method for solving flow problems in complex geometries. And that is the reason why the industrial strength commercial CFD packages are based on finite volume method, wherein we can import a mesh which is generated using an unstructured grid generator for finite element analysis and solve our problem. Now, let us have a brief look at the overall solution process which is adopted in finite volume method. We have already seen part of it. So, the first part of the solution process using any discretization scheme, whether it is finite difference, finite element or finite volume method, is one, discretize the solution domain by a grid or a mesh. So, that is what we will do even in the case of finite volume method, discretize the solution domain by a grid, that is a set of finite volumes, and we have to define what we call computational nodes at which our problem variables are to be evaluated. Now these computational nodes, they need not coincide with the vertices or the corners of finite volumes, which we will see shortly. Now once we have done this discretization, the next step is apply the integral form of conservation law to each finite volume. Now we have already seen there are two types of integrals involved. There are surface integrals and volume integrals, which are in terms of our unknown variable. So we can't evaluate those integrals exactly. So what we need to do is we have got to approximate those integrals. So approximate the surface and volume integrals using appropriate quadrature formula in terms of the function values at computational nodes, because these are the ones which are of interest to us in our solution process. We want to obtain the function values at computational nodes, and in terms of these values we would approximate the surface as well as volume integrals. So once we do that, we would be able to convert the integral form of conservation laws applied to a finite volume into a discrete algebraic equation. And once that is done, all that we need to do is collect the algebraic equation for all finite volumes to obtain a system of algebraic equations in terms of the unknown values of the variable at computational nodes. And depending on the nature of that system, we can use a linear solver or a non-linear solver. So all that we need to do is solve the resulting set of equations to obtain values of the variable at the computational nodes, and if we want to obtain what we call dependent variables, for instance the ones which are defined in terms of gradients of our basic variables, that can be done at the post processing stage. So if we look back to the way we discussed the solution process for finite differences, the similarities are obvious. In fact, the last step would be the same for finite difference or finite volume or finite element method. It's only the first three steps which might differ from one discretization procedure to another. Now let us have a brief look at the basic types of finite volume grids which are employed. Now here what we mean by grids is not what type of unstructured grid or structured grids we are going to use. This classification is based on our choice of the computational nodes. So there are two common approaches to finite volume discretization, basically to the choice of computational nodes. The first one is what we call cell centered approach. Now in cell centered approach, what do we do? The CVs are defined by a suitable grid and computational nodes are assigned at the CV center. And the second approach is what we call face centered approach. Now here what we do is we choose the nodal locations first, choose our computational nodes, and CVs are then constructed around them so that the CV faces lie midway between the nodes. But there is one limitation, that this method can be used only with structured grids. Now let us have a geometric look at both these approaches. Get back to our board and see both of these approaches. The first one is cell centered grid. Finite volume grid. So whatever our problem domain might be, suppose for the sake of simplicity let us take one rectangular domain, discretize it into a set of finite volumes. Suppose you have taken these rectangular finite volumes. Now choose the centroid of each one of these. The centroids are the ones which are now our computational nodes. So as you can say, this process is fairly simple. is applicable to not just the structured grid. Suppose we had an unstructured grid over a fairly complex, like arbitrary domain, and we had used an unstructured mesh generator to divide it into a collection of non-overlapping finite volumes, which could be triangular, which could be rectangular. Now these finite volumes could be of arbitrary shape. Okay, generated using our favorite unstructured mesh generator program. We can have a collection of elements of any type. Now, to define our grid, what we need to do is take any shape and just find out where the centroid is. Now, finding the centroid of a geometric shape is a fairly straightforward operation, because we know the coordinates of the vertices, and in terms of the vertex coordinates, we can easily determine what would be the centroid of these cells. Okay, so generating a cell centered finite volume grid is a fairly straightforward. So we had a look at two examples, one on structured mesh, and other one in the case of unstructured mesh. Now let us have a look at the second one. Second one, we said, look, we are going to now define our computational nodes first. So let us say this is our choice of the computational nodes. And next, what do we do? Draw the midplanes, for instance, between two, just for the time being, connect these with dotted lines. We need to find out the midplanes between these nodes, which will define our control volume surfaces. So this is one of the midplane, this the midplane here, this is the midplane. Similarly, midplane between these two, so this could be, let's draw here. So these are the midplanes. And now the intersection of these surfaces, that is what will give us the finite volume. For instance, if you look at this particular node, now so the corresponding finite volume. Now you can clearly see in this particular figure, or its adjoining finite volume, the computational node is not at the centroid of our finite volume. So this is our face centered arrangement, and you can clearly see that we can generate such faces which will intersect and lead us to non overlapping finite volumes only if our nodal arrangements were in a structured fashion. So this face centered approach can be utilized only for structured grids. The cell centered approach can be used for both structured as well as unstructured finite volume formulations. Now one more thing which we can say here, let us go back to our structured grid case. Let us take one computational node. The value at this particular computational node, that would in a sense represent the average over the finite volume. Okay. So, thereby what we expect is that the representation of our unknown variable can be done to a much greater accuracy in the case of cell centered finite volume approach. But in our formulation of our integral equation, we need some surface integrals where we need to evaluate certain fluxes which are involved in the gradient terms. So, if you look at the evaluation of those gradients, they would involve the derivatives. Derivatives can be obtained at the cell faces with greater accuracy in the case of our face centered approach, because now we have got two computational grids, and this face center, that particular point is midway between the two. So, we can use very accurate central difference approximation for evaluation of the derivative at this face center. But nevertheless, because of the versatility of the cell centered approach, that it can be used for both unstructured as well as structured grids, the cell centered approach is the one which is used more commonly. So, that is a summary of what we just discussed. The cell centered nodal value represents the mean over the control volume to a high accuracy than face centered approach. However, CDS approximation of derivatives of CV faces are more accurate in face centered approach. And we have already seen the cell centered approach can be used with structured or unstructured grids, whereas the face centered approach can be used only with structured grids. Hence, most of the time it is cell centered approach which is used. So, this cell centered approach is more commonly used in finite volume formulations. Now, if you are dealing with structured grids in finite volume analysis, also we use a notation fairly similar to what we had already seen earlier in the case of finite difference method. When we defined our computational molecule, we used what we called a compass notation. So, this compass notation can also be used for structured Cartesian finite volume grids. And now in this case, in the case of finite volume formulation, we will have two sets of things which we need to look carefully. We have got our computational nodes. So, computational nodes are denoted by uppercase letters. This capital P is our central node or the centroid of the finite volume of interest to us. E is the easterly neighbor node, W is the western neighbor node, N is northern node, S is southern node, T top and B bottom node, and so on. And the plane faces, that is the faces between let us say the computational node P and E, the face of our control volume or finite volume towards, or so that which lies between nodes P and E, that is denoted by a lowercase letter e. So, similarly rest of the face cell faces, we use the corresponding symbols depending on the directions. So, plane faces denoted by lowercase letters corresponding to their directions by small e, small w, small s, small n, small t and b with respect to the central node. To explain a bit more clearly, let us have a look at the 2D situation for a compass notation. So, let us first draw a structured grid. In 2D, so x direction, y direction, and suppose this is our central finite volume with reference to which we want to illustrate our compass notation. So, the centroid of this finite volume, that is what we will denote by capital P. and the corresponding faces is xi, xi plus 1, xi minus 1. Similar, this is yj, yj plus 1, xi plus 2, yj plus 2, and so on. The computational nodes to the right, which is in the eastern direction with respect to P, we would use a symbol capital E. The computational node is west, that would be denoted by symbol capital W. If we had, let's extend it further, the nodes to the east of us would use two capital letters, capital EE, and so on. Similarly, in the y direction, the node in the positive y direction, this will be called the northern node. This becomes NE, then the computational node NW. In negative y direction toward the southern side, immediately to the next of it, this becomes our computational node capital S. This is computational node capital SW, capital SE, so it will become capital SEE, NEE, and so on. Now let us have a look at the faces. The finite volume phase between the nodes P and E, that is to the east of P, that would be denoted by symbol small e, small s, small w, small n, and so on. If we had a 3-dimensional thing, the one towards top of it, that node would be represented by symbol capital T, and the phase between P and T, that would be denoted by symbol small t, and so on. So this is a compass notation which would be used with structured finite volume grid. In the case of unstructured finite volume grid, we would go back to the lessons which we would learn from finite element method. We would use the element connectivity instead to denote these faces and surfaces. Now next let us have a look at the approximations which are involved in finite volume formulation. So what we saw, that integral form conservation law, we have both surface and volume integrals, and these integrals involve unknown function values, and hence we cannot evaluate them exactly. In fact, they cannot be evaluated because they are in terms of the unknown function values. So for finite volume solution, what do? We will assume that our unknown function is specified at computational nodes and use those values, or the function values at computational nodes, to obtain an approximation for these integrals using appropriate quadrature formula. So now let us first have a look at the schemes for the surface integral. How do we approximate the surface integral? Now let us take a generic function f, and we want to find out the flux of this net flux through CV boundary. This is sum of integrals over CV faces. So integral of S f ds is equal to summation over k integral over sk f ds, where sk is a phase, one particular phase of our control of volume or finite volume. Now here our f could be a component of a convective flux or a diffusive flux in the direction normal to the control volume phase. So if we can obtain a quadrature formula of one of these phases, let us say k is equal to E, that is eastern phase, we can derive analogous formulas for rest of the phases as well. So now let us take that eastern phase as our example phase. So suppose we want to calculate the integral exactly, then we require f everywhere on the surface of the eastern face SE. However, this information is not available. In fact, where we know in terms of computational node values, that is only specified at the computational nodes. So, we have to obtain an approximation for this f. So, to obtain an approximate value of the integral, we have to use what we call two levels of approximations. The first one is approximate the integral in terms of the variable value at one or more locations on this cell face SE. That is the first step which we have to perform. Now, that value itself would be unknown, so that has to be approximated, that is cell face value, that has to be approximated in terms of the nodal values, because nodal values are the ones which we are going to solve for. Those are available and those are the ones which will come in a final discrete algebraic equations. So, now let us approximate the cell face values in terms of our values at computational nodes or CV center values. So, these are two levels of approximations which would be involved in evaluation of all the integrals. So, we will first have a look at the first approximation, that how do we approximate the integral in terms of the values of variable f at one or more locations on the cell face. The first approximation scheme is called midpoint rule. It looks extremely simple, but it is extremely useful and powerful. It is the one which is used almost exclusively in unstructured finite volume codes. So, approximate the integral as the product of the integrand at cell face center and the cell face area, that is integral of f ds at this face SC can be approximated as the value of f at the center of this face, which we will denote by f subscript e, multiplied by the area of this face. So, even this simple approximation, it is of second order accuracy if value of f is known at the location E, where this E denotes the center of the face SE. So, if you want to preserve this second order accuracy, we have to obtain Fe in terms of the values at the computational nodes to at least second order accuracy. And how do we do this? This part we will have a detailed look in our next lecture, wherein we have discussed different interpolation schemes. Now, this so called very simple midpoint rule, it is widely used in 2D as well as in 3D. In fact, in 3D unstructured formulations, this is the scheme of choice. Next could be that for two dimensional problems we can use trapezoid rule, which will require the values of f at CV corners, and this is given by integral f ds is approximately equal to s by 2 fne plus fse. This basically what do we do is that we want to approximate this value over the cell face as an average of fne plus fse, multiply that by area, and this is what would give us the value of this surface integral. If you want a higher order accuracy, trapezoid scheme has again got the second order accuracy. If you want a higher order scheme in 2 dimensions, we can use what we call Simpson's rule. So, it provides a fourth order approximation, and here we will have values at 3 points involved. The function values at northeastern point, northeastern corner, the center of the face E, and southeastern corner. So, in terms of these values, the integral is given by integral SE f ds is SE by 6, value of f at northeastern corner plus 4 times value of f at the center point of the face plus the value of f at the southeastern corner. Now, fne, fe and fse, these would have to be calculated using the nodal values at the computational nodes. So, if we want to preserve the fourth order accuracy of the Simpson's rule formula, we have to evaluate fe, fne and fse with at least fourth order accuracy. So, in 2D, yes, we can have fairly good amount interpolation formula, but in 3D we would find the Simpson rule to be too demanding to use. So, we will stick to a midpoint rule in most of the 3-dimensional finite volume analysis. Next is approximation of a volume integrals, because there were 2 integrals in our conservation rule which involved volume integrals. So, the most popular and the simplest method of evaluation of volume integrals is again our midpoint rule, that is, take the value at the centroid, multiply that by the volume, and that gives us the approximate value of the integral. So, if we denote by capital QP the integral of q d omega, so this is approximately equal to q bar delta omega. In fact, this is equivalent to q bar delta omega, where q bar is an average value over the cell, and it can be approximated as value of q at the centroid of the cell multiplied by the volume of the cell. Now, once again this simple approximation scheme has got second order accuracy. In fact, it will lead to exact integration or exact value of this integral if q were constant or linear. So, once again I would like to emphasize that this particular formula, which looks utterly simple, is the one which is used very widely in finite volume analysis. But suppose you are interested in higher order methods, and if you want to develop fairly complicated code, yes, you can do that. You can obtain higher order approximation of the volume integrals in terms of the values of q at more locations than just the center of the CV, and these values can be obtained by interpolating the nodal values, or we can use the shape functions very similar to what we will see in our finite element module later on. For instance, let us say if we are dealing with 2D volume integral, which is essentially an area integral. So, we can use a biquadratic shape function for approximation of variable q. Qxy can be given in terms of the coordinate values. So, a0 plus a1x plus a2y plus a3x square plus a4y square, a5xy plus a6x square y, and so on. So, now these coefficients which we have got a0 to a8, they are determined by fitting the function to the function value at 9 locations. We have got these 9 unknowns. So, we will fit them at 9 locations, and we can obtain the value of these coefficients in terms of the nodal values of the function. On a Cartesian grid, if you perform the integration, you will get a simplified form that QP is given by delta x into delta y within brackets a0 plus a3 by 12 delta x square plus a4 by 12 delta y square plus a8 by 144 delta x square delta y square. And if we had a uniform Cartesian grid, the equation becomes even simpler. So, it can be reduced to this form. So, QP is equal to q d omega, that's approximately equal to delta x delta y by 36 within brackets 16 q at p plus 4 times q at n plus q at s plus q at w plus q at e. So, q small n small s small w small e, they are the values with respect to phase centers, plus q at northwestern corner plus q at northeastern corner plus q at southwestern corner and q at southeastern corner. You can easily appreciate that obtaining each one of these in terms of the nodal coordinates would be fairly involved task, because if you want to retain the 4th order accuracy of this formula, we have to approximate each one of these q values to at least 4th order accuracy, which is not a mean task. So, in practical analysis, we would basically restrict ourselves to midpoint rule integration. So, this way we would stop in this lecture. In the next lecture, we will have a look at the interpolation schemes whereby we obtain the values of variables at face centers or the corners in terms of the nodal variables. In the meanwhile, if you are interested, you can look at these references. Book by Chung, it also gives you some details about finite volume method. Similarly, book of Furziger and Perick, it contains 2 chapters on finite volume analysis. And there are two books which are exclusively devoted to finite volume method, that's Versteeg and Malal Sekhar's book. This is Introduction to CFD based on finite volume method. Similarly, you can also pick up the classic book of Patinker on CFD, which is again based on finite volume method.